Mercury is often known as the smallest planet, the one closest to the Sun, and a world of extreme heat. However, discoveries from NASA's Messenger spacecraft have opened an entirely new perspective on this planet. It is not the hottest planet in the solar system. In fact, nighttime temperatures on this planet can drop below -170 degrees Celsius. Why does a planet so close to the Sun experience such dramatic temperature differences? Findings from Messenger reveal that Mercury has a thick rocky mantle and a massive iron core that makes up nearly 75% of its volume, making the planet far more unique and complex than we once imagined. With every close encounter with Mercury, we uncover new discoveries. From a surface scarred by impact craters to mysterious shadowed regions at the North Pole, where sunlight has never reached. Let us explore these mysteries and discover why Mercury is one of the most remarkable planets in the universe. Imagine, for a moment, standing upright on the surface of Mercury. You would not be pressed firmly against the ground as you are on Earth. But you would not feel nearly weightless like on the Moon either. Your weight would drop to about 38% of what it is on Earth. A sensation similar to standing on Mars. This feeling defies intuition because Mercury is far smaller than both Earth and Mars. A planet that small should, by all logic, feel much lighter. Yet it is precisely this mismatch that opens the door to one of the strangest stories in planetary science. In terms of raw numbers, Mercury has a radius of about 2,440 kilometers, only around 38% of Earth's radius. Its volume is more than 18 times smaller than Earth's by simple reasoning. An object that's small should have low mass and weak gravity. But Mercury's average density is about 5.43 grams per cubic centimeter, nearly the same as Earth's. This value comes from direct orbital measurements based on how the spacecraft's velocity changes under the planet's gravitational pull. When scientists pieced these data together, an unsettling picture began to emerge. Mercury contains far too much mass for its size. A surface gravity of about 3.7 meters per second squared is enough to keep you firmly grounded and stable as you move. But why can such a small planet exert a pull that comes close to Earth's? The answer lies far beneath the thin, rocky crust beneath your feet. In other words, Mercury is more like a massive metal core wrapped in a thin shell of rock than a fully developed rocky planet. If you could slice Mercury open and look inside, you would see an iron core occupying most of its volume, extending almost to the surface. This explains why such a small world can have such high density and surprisingly strong gravity. But this structure is the fingerprint of an extreme formation history. In the early, chaotic stages of the solar system, young planets constantly collided, merged, or were torn apart. For Mercury, scientists proposed two main scenarios. The first suggests that a colossal impact stripped away most of the planet's original rocky mantle, leaving behind a dense metallic core. The second proposes that Mercury formed in an intensely hot region close to the Sun, where lighter materials struggled to condense, causing the planet to be metal-rich from the very beginning. The common conclusion is unavoidable. Mercury is the product of a violent, unforgiving process. Weight on Mercury reminds us that size does not define essence. A small world can still carry the mass of a brutally turbulent history. And yet, if this sense of heaviness alone already makes Mercury feel alien, it is still not the greatest challenge it poses to human life. The first and most fundamental danger is the near-total absence of an atmosphere. Mercury does not have an atmosphere in the familiar sense. What surrounds the planet is only an extremely tenuous exosphere, where individual atoms, such as sodium, potassium, oxygen, helium, and hydrogen, exist in isolation. Constantly stripped away and replenished by the solar wind. Surface pressure is almost zero. There is no air to breathe, which is obvious. But far more dangerous is the fact that the human body cannot survive in a vacuum. If a protective suit were breached, even for a moment, bodily fluids would begin to boil due to the sudden drop in pressure. Soft tissues would suffer severe damage, and consciousness would be lost within seconds. This is not speculation, but a direct consequence of the laws of thermodynamics and human physiology. However, even if humans were perfectly shielded from the vacuum, Mercury still wields another equally ruthless weapon: extreme and unstable temperatures. Without an atmosphere to retain heat or distribute energy, Mercury's surface responds directly to solar radiation. In regions facing the sun, surface temperatures can exceed 430 degrees Celsius. This is not merely hot. It is hot enough to rapidly destroy most organic materials and weaken many industrial alloys unless they are specially engineered. By contrast, when the same region rotates into prolonged darkness, temperatures plunge to around -173 degrees Celsius, colder than the environment of Earth's orbit. What makes this truly terrifying is the enormous temperature range and the complete absence of any middle ground. On Earth, the atmosphere and oceans act as thermal buffers, slowing and softening changes. On Mercury, no such buffer exists. The transition between heat and cold is direct, brutal, and unforgiving. For humans, this means that any activity outside sealed environments would be severely restricted. A base on Mercury, if it were ever to exist, would require flawless thermal control at all times. Yet even if humanity could master vacuum and temperature, Mercury presents another threat. More subtle, but harder to escape: solar radiation. Mercury orbits the Sun at an average distance of only about 58 million kilometers, far closer than Earth. At this distance, the intensity of radiation the planet endures is many times greater than what life on Earth evolved to withstand. On Earth, a thick atmosphere and a strong magnetosphere act as shields, deflecting charged particles and absorbing much of the harmful radiation. On Mercury, those shields are nearly absent. Mercury does have a magnetic field, but it is weak, only about 1% the strength of Earth's. And it is compressed tightly against the surface by the solar wind. As a result, high-energy particles from the Sun can reach the surface far more easily. For humans, this represents a slow but inevitable sentence. Ionizing radiation damages DNA, increases mutations, weakens the immune system, and injures internal organs. No massive radiation event or rare solar flare is required. Prolonged exposure alone is enough to cause severe consequences. What is most troubling is that these dangers do not exist in isolation. They compound one another. A spacesuit on Mercury would not only need to be perfectly sealed to maintain pressure, but also provide flawless thermal insulation and effective radiation shielding. It would have to function continuously, without error. In an environment where solar energy is both the sole source of survival and a constant threat. On Earth, humans can survive brief technical failures. From the perspective of planetary science, Mercury forces us to confront an uncomfortable reality. Not every rocky planet has the potential to become a second home. Even with a familiar size, even with a metallic core, even after remaining stable for billions of years, a planet can still be completely hostile to complex life. Habitability depends not only on position within the solar system, but deeply on a planet's formation history and evolutionary path. Mercury is the product of a harsh evolutionary journey. One in which nearly every protective condition for life was stripped away very early on. And yet, within this deadly environment, Mercury preserves something else that is extraordinary. With no atmosphere to erase the past and no plate tectonics to recycle the surface, every event that has ever occurred is etched directly into the ground. Impacts, eruptions, and ancient upheavals remain clearly recorded, frozen in place. Orbital data show that Mercury has one of the highest impact crater densities among the rocky planets. There is no plate tectonics to push old crust downward and create new layers. No thick atmosphere to erode the surface, and no liquid water to wear the landscape away. An impact crater formed more than 4 billion years ago can still remain almost perfectly preserved today. What makes this planet both terrifying and fascinating is the coexistence of external violence and internal energy. Between regions densely packed with craters lie vast lava plains, stretching for hundreds, sometimes thousands of kilometers. Imaging and spectroscopic data from NASA's Messenger spacecraft reveal that much of Mercury's surface was once flooded by basaltic lava during the planet's early history. This indicates that, despite its small size, Mercury once possessed enough internal heat to sustain prolonged volcanic activity. The existence of these lava plains carries a deeper meaning. It shows that Mercury once responded to being struck when its crust was fractured. Internal forces surged upward, filling the wounds with molten lava. Mercury's surface is therefore the result of a violent dialogue between outer space and the planet's inner depths. Nowhere on Mercury demonstrates this more clearly than the Caloris Basin, with a diameter of about 1,550 kilometers. Caloris is one of the largest impact craters ever recorded in the solar system. Its scale is comparable to the width of the entire continental United States. The impact that created Caloris did far more than carve a massive hole. It released enough energy to melt rock on a planetary scale. The basin's rim rises more than 2 kilometers high, and geological evidence suggests that after the impact, lava flooded the basin floor, creating smoother plains at its center. If you were to stand on the rim of Caloris today, you would be standing before the aftermath of an event that may have shaken the entire planet. Yet on the exact opposite side of the planet, scientists have identified a bizarre region known as the Weird Terrain. This is an area where the surface is crushed and jumbled, with rock blocks tilted and shattered in chaotic ways that follow no familiar geological structure. Based on planetary seismic models, shock waves from the Caloris impact traveled through Mercury's entire interior, converged at the antipodal point, and shattered the crust there. On Earth, geological memory is buried, reworked, and partially softened by natural cycles. On Mercury, every crater marks a moment of violence. Every lava plain is a desperate response from internal forces. Every scarp is a sign of slow contraction over time. Mercury is not merely a dead planet. It is a living archive of the early era, where rocky worlds were shaped not by stability, but by constant violence. Within that battered surface, among ancient craters and frozen lava, Mercury hides another paradox that challenges every instinct. Mercury has long been considered a place where water could not exist in any form. Too close to the sun, too hot, too extreme. Every simple model led to the same conclusion. All volatile substances, especially water, should have evaporated and been stripped away very early on. And yet, Mercury itself is the world that forced science to pause and accept a difficult truth. Water not only exists there, it exists in a stable form. It began with a puzzling signal in the late 20th century. When radar observations from Earth detected unusually strong radar reflections at Mercury's poles. This type of reflection had already been observed on the Moon and was linked to water ice. When NASA's Messenger spacecraft entered orbit around Mercury in 2011, suspicion gave way to data. Messenger carried neutron and gamma-ray spectrometers along with high-resolution cameras, allowing detailed observations of the polar regions. The results revealed deep craters at both Mercury's north and south poles that never received direct sunlight. The reason lies in Mercury's extremely small axial tilt, almost perfectly upright relative to its orbital plane. As a result, the Sun always sits very low on the horizon at the poles. Craters that are deep enough are never illuminated directly. Within this permanent darkness, temperatures can remain below about -170 degrees Celsius, well under the threshold required for water ice to remain stable over long periods of time. Neutron measurements from Messenger showed very high concentrations of hydrogen in these regions, a clear signature of water. Further analysis indicated that many craters contain nearly pure water ice, sometimes covered by a thin layer of dark material, possibly organic compounds or carbon-rich substances, which help shield the ice from slow sublimation. These are not random traces, but thermally stable ice deposits. Current estimates suggest that the total amount of water ice at Mercury's poles is far too large to be dismissed as a temporary remnant. Water on Mercury may have been delivered through multiple episodes by water-rich meteorites, comets, or even ancient outgassing processes from the planet itself. While the exact origin is still under investigation, one fact is now clear. Mercury is capable of retaining water on geological timescales. Mercury demonstrates that the presence of water does not depend solely on average distance from a heat source, but also on microtopography, illumination geometry, and a planet's thermal history. A world can be scorching across most of its surface and still host cold traps where water is preserved. This discovery has forced scientists to reconsider how resource potential is evaluated across the entire solar system. Water on Mercury survives only because of extraordinarily specific geometric and dynamical conditions. Conditions tightly bound to the way the planet orbits the Sun and how its metallic core interacts with the surrounding space environment. To understand why these cold traps can remain stable for billions of years, and why Mercury is such a world of unusual timescales and magnetic behavior, we must take one more step forward. Let us begin with what seems most obvious: time on Mercury, where a single day is longer than a year. This is the result of a rare dynamical state known as a 3-to-2 spin-orbit resonance. Mercury rotates 3 times on its axis for every 2 orbits it completes around the Sun's. This state is maintained by the Sun's powerful tidal forces acting on a planet with a massive metallic core and an uneven distribution of mass. The consequences of this 3-to-2 resonance are not confined to equations. If you were standing on Mercury's surface, you would directly witness time behaving in unfamiliar ways. At certain longitudes, the Sun does not move steadily across the sky. It can slow down, nearly stop, and even move backward for a short time before resuming its familiar motion. This phenomenon, often called a double sunrise or the Sun's retrograde motion, is the result of a delicate interaction between the planet's rotation rate and its orbital motion around the Sun's. On Mercury, there is no familiar day-night cycle for the body to rely on. No gentle transition between light and darkness. If humans were to live there, their biological rhythms would lose any natural anchor. Messenger confirmed that Mercury possesses a true intrinsic magnetic field, with a strength of about 1% of Earth's. Weak as it is, the existence of this magnetic field carries profound implications. A global magnetic field can only be sustained if a planet contains a moving, electrically conductive metallic core, typically molten iron. This means that Mercury's core, despite the planet's small size, has not fully solidified. It still retains enough heat and motion to power a planetary dynamo. Yet Mercury's magnetic field is unlike that of any other rocky planet we know. It is asymmetric, with the magnetic axis significantly offset toward the north relative to the planet's center. This creates a distorted magnetosphere, where shielding is unevenly distributed across the surface. As a result, Mercury experiences one of the most intense planet-solar wind interaction environments ever observed. When its strange sense of time and its unusual magnetic field are considered together, Mercury emerges as the logical outcome of extreme conditions. Close proximity to the Sunday, a massive metallic core, a significantly eccentric orbit, and an evolutionary history unlike that of any other rocky planet. What humans regard as normal, a 24-hour day, a year longer than a day, a strong and symmetric magnetic field is, in reality, a rare special case, not a universal rule of the cosmos. Before the 21st century, Mercury was almost a forgotten planet in planetary science. Difficult to reach, difficult to observe, and widely assumed to have little left to reveal. To enter orbit around Mercury, a spacecraft cannot travel directly. It must continuously shed energy, fighting the sun's powerful gravity. Through a complex sequence of gravity assists from Earth, Venus, and Mercury itself. Messenger became the first spacecraft in history to orbit this planet. And it marked a turning point that transformed Mercury from a faint dot into a world with a rich and complete scientific record. Over 4 years in orbit, Messenger transmitted more than 200,000 images, covering nearly the entire surface of Mercury and enabling the first global color maps of the planet. More importantly, Messenger did not simply confirm what science believed, it repeatedly challenged it. It revealed that Mercury is not a simple rocky planet, not a world that has fully cooled, and not a lifeless remnant of the past. Yet beyond their specific scientific goals, Messenger and BepiColombo together represent something larger. A shift in how humanity approaches the universe. Messenger showed that Mercury is far from simple. BepiColombo will show that it was never simple at all. But the final question does not lie with the planet. It lies with us. Are we ready to accept that the things not taught in school may be the true keys to understanding the solar system and, more broadly, to understanding our fragile place in a universe that was never designed for anyone's comfort? Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.